Hi YouTubers, here is the STM8L discovery board. I'm checking out the external IRQs and I'm debugging that thing here. And this is the Jerry Ellsworth's arbitrary frequency and quantization DAC project. And here is my pin map of that discovery board here. This and this is with the Discovery STM8L chip, and I'm using here, the good stuff is it has an internal clock, but all the good parts here, they are gone for the LCD stuff here, and there's not a lot of ports left to experiment on that. And so I decided to do some stuff with the analog port. And the analog port is the ADC, and it can be a ADC port or a DAC port. And this is the all included in the description from the manufacturer. And I want to check out here this one. This is to start it. And here you can start the debugging session, and now you can see it's running at 0 o'clock, and after this is the interrupt kicks in and the timer gets started via the interrupt. And the normal interrupt is this here, and if you want to have a key turn, the code is inside, it makes a reset and your code is inside. It's flashed already, and that's the turnkey solution and a standalone solution. You can plug it out and put the battery on or something, and the code is inside the chip. It's not so complicated like PIC controllers or something. The flash is already done. And this is a little example here. A triggering on the rising edge with the external pull down, the blue pin, and clear the interrupt with the black flag. And here's some experimental stuff I do. Okay, that's the scratch map here I have. And that's the external ports I'm using. And I want to do a PSOC project with this externally. And I'll show you here in a minute the ripple counter. This is some for my documentation, the rising edge here, and you can test the interrupt latency at that time, and I check it out how it works. And that's the symbols for the rising edge, falling edge, or any edge or level. That discovery board has a level interrupt, not falling edge, and falling edge and level. Very complicated. That's the interception here for the wait event interrupt routine. And then after this it passes, it's direct to the interrupt controller. And that's what I want to check it out the next time. That's the ripple counter. And here I'm triggering on the Q14 and Q13. And they open and close the gates here like a switch. And this is the analog part here. And here's the shunt resistor. I had trouble with this, and so I decided to put it in the upper, the jumper in the upper position. And so I can generate an interrupt here via that glitch here. and this is the pull down, and the interrupt goes on rising edge because the current flows being this way and initiates a rising edge. And so I decided, and here's the analog part, and this is a measurement circuit, and you can trigger that by this Q and invert it, and this is here switched over this way, and that's a very tricky stuff, I think, because I'm very new to it. This is the board what I'm using. It's always the ripple counter, what you can do with the ripple counter, and so you can generate external interrupts without CPU invention. It's really external, and that's very important. It's an external interrupt. It has nothing to do with the CPU environment. It bangs in, it kicks in, and you get the answer here. In the interrupt control, you can measure, example, the interrupt latency, I think. With this trick, you trigger on that, wait how long the interrupt latency takes, and then I clear the counter via a reset. And that time is the quantization for the interrupt latency, or any kind of stuff you want, but it's really external interrupts, and that's what I want to show you here. Thanks for watching.